in this GAN program. So it's a tutorial session. So maybe he will discuss some maybe some maybe
I
one
mean,
problem or maybe
some I want to touch
step.
on some
Yes.
stuff. Yes, 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 yes.
So
So
so please you can
two
say.
stuff I want to touch on, which are technical but not in the formal presentation I made, and I wanted to clarify it. One is the minimal convex sets, okay, and how everything that was done depends on the minimal convex set. So I wanna show you something there, and then I want to move to the idea of compactness of the balls. That's very important. The other one is old, 1965, 1975, and so on and so forth. But the one I'm going to be talking about, that's important. I want you to pay attention. So it's more like exercise, more like tutorial than the formal stuff, okay? Than the formal stuff. So let's go first to the first part. So what do we have? We have, okay, let's stay in the 1965 mind. So we have K, which is convex, not empty, subset of a Banach space. And we assume that K is compact. Okay? And we take T, which goes from K to K, which is non-expensive. Okay? If K is reduced to 1 point, then we have fixed point. So of course this problem is interesting if K is not reduced to 1 point. Which is equivalent to say that the diam of K is greater than 0. Of course, you may ask me, is it bounded? Yeah, because it's weakly compact. Since it is weakly compact, it is bounded. Okay? So this is the general picture of 1965. Okay? Some people did not go down to K, but that assumed that the space is reflexive. And K is only bounded, closed, convex subset. Okay? So if it is bounded, closed, convex subset, it is weakly compact. From that, from what I am saying right now, came two properties. Okay? Two properties. From this point I'm telling you, came two properties. One is what is known as fixed point property, meaning what? That you have a Banach space for which any bounded, closed, convex subset has the fixed point property for non-expensive mapping. Pay attention. I did not say what? That the space is what? Nor that I said that K is what? Weakly compact. I did not. So what did they say? This is known as what? Did they say weakly fixed point property or fixed point property? What did they say?
Weak fixed point property.
Ah?
Weak fixed point property.
I said weak?
Yes.
Good job. Some people are following me. I meant to lead you to a mistake. But anyway, so if this property I just described is fixed point property. The weak fixed point property, if you assume that K is what? Weakly compact. Now, there is a paper that was published by a student of Brayley, an Australian mathematician who is now in Illinois, and his name is Chris Lehnar. And Chris Lehnar likes always to mislead the people. He's young, by the way, he's not old. And when they talk about fixed point property, if you are not careful, they mean the one for bounded, closed, convex subset. Okay? They don't mean the one for weakly compact, convex subset. These two properties are totally different. So, of course, which one is important to us since 1965 and before? It was the one which is known as weak fixed point property. The problem is many of us do not use weak fixed point property and fixed point property. And therefore, it misleads the reader if you are not careful. If you are not careful. Okay. So I'm not going to work with what? With the one for bounded, closed, and convex. I'm working with weak compactness. And the reason is because if I don't have weak compactness, I am not able to generate the minimal invariant set. See? That's the problem. So the proof should be constructive if I'm dealing only with what? With what? With bounded, closed, convex subset. It has to be constructive. You cannot use zone, period. Which takes us to another problem altogether, which is constructive, non-constructive problems. Under what axioms are you working with? Axiom of what? Choice, no, yes. There is all this discussion. Okay? In fact, there was a Turkish student of Kirk who worked his PhD on this. So there is a school of people working on this problem, okay, which is constructive, non-constructive proofs. Okay, so now, what does zone tell us? So if I take the family F of C closed convex subsets of K, not empty and invariant. Okay? So this family F is not empty because it contains K. Yeah? If I order it ordered by inclusion, okay, and because of weak compactness, then any chain or totally ordered subset of F, the intersection is not empty, that's weak compactness. To be invariant, that's easy because each one of them is invariant. Just set theoretical approach. And therefore, by zone lemma, we have what? Minimal element. So here, zone lemma applies. Okay? Which gives us what? Minimal elements. Now, these minimal elements were used by, what's his name? If you remember the lectures, by Browder in the second paper, not in the first paper. Okay? When he was in Hilbert, it's a different approach. But in the second paper, he used the minimal element, number one. And also, it was used by Kirk. The problem is that in the proof by Browder in the second, it's inherent. He did not know about normal structure property. Nobody knew about normal structure property. And therefore, it was more about what? Kirk, who exhibited the properties, some properties of the minimal element. Okay? Therefore, the main question is, so what is the main problem? And believe me, is the main problem. What are the properties of the minimal elements of F? That's it. 1965, moving forward till today. Some of them are easy to prove, which I will show you in a second. Some of them are not easy to prove, and basically we don't know anything else. When we have information, so let me say, for example, just throw it at you and you will understand where I'm heading with this. Assume that the minimal element is a star. Okay? Assume that we prove that the minimal element, the minimal convex set invariant by T, is a star. Then I have a theorem. If the convex closed sets are not stars in the space, then we have fixed point. Do you see how they approached it? If you give me information on the minimal element, automatically I will give you what? A fixed point theorem, by failing the property that you have there. This will explain two things: the normal structure property and the asymptotic normal structure property, both. Why it took long between the two, I will explain in a second. But basically, that's what it is. So if we know a little bit more about the minimal, it will advance us. How? At understanding the fixed point property. Because the minimal, what does it mean? It's just set theoretical. Is the least convex, bounded convex set invariant by T. So you have T and you have the set. There's nothing else. Except that T, of course, is what? Is non-expansive. Which brings me to another problem altogether, which is AR with ANR. Maybe I'm misleading you. Absolute retract and absolute non-expansive retract. You know what? This would take me completely away from what I want to say, and we don't have time. So let's stick to this. Now, what are the known properties? I will start with A and B I showed you here, and these are the properties that Kirk used in 1965. Okay? So what is the first one? So, of course, the problem is interesting if the minimal element is not reduced to what? Because it's invariant. So here, we are going to assume what? We assume the minimal element is not reduced. We know it's not empty to one point, because otherwise there is nothing to prove. Okay? So we have C, minimal, T from C to C. Minimal. Yeah? The first property was known both to Browder and to Kirk. How? And I showed it to you. So we have T of C included in C. Conv of T of C is included in C, because C is convex and closed. Do we agree? And the conv is the smallest closed convex set which contains the set. Okay? It's the intersection of all of them, in fact. Now, let's take T of that. T of conv of T of C is included in T of C. Yes? And T of C is included in the conv. Yes? Therefore, the conv of TC is invariant. It is closed, convex. Therefore, by minimality of C, by minimality of C, we have C equal conv of TC. Let me make a comment here. I don't want you to take it for granted as being a simple proof. There is something hidden here that is beyond what you saw. The proof is easy, but let us think of it from outside the box, not just to follow the proof and it's a done deal because it's easy. Okay? Does it remind you about Karisti? Huh? How he got there through steps that are very elementary. But if you think about it outside of the box, it becomes very interesting. It's like opening the door to some big forest. Remember the two trees that hide the big forest? So did you notice here I was just using set theoretical approach? Completely set theoretical approach. Of course, you have to ask me, what is the conv? I use the conv. So once I have the concept of the conv in abstract way, okay, the proof is entirely what? Set theoretical. Are you with me? This comment, I'll come back to it in the second part, okay? So this is the first result, that's the famous A in my presentation. That T of C generates C. That is what it means. So C is captured by the image of C by T. So T of C generates C. Okay, now let's go to the second property. This is Kirk now. Huh? Of course, our friend Browder, what did he do? He used uniform convexity to build another set which is invariant with the diameter that is less than the diameter of C. That's what he did. But he never heard of normal structure property. Remember, that was Brodsky-Millman, and Kirk is the one who brought it in force to the people working in Banach spaces. They didn't know about this. So now fix X in C. And let's look at R0, which is basically the Chebyshev radius of X of the set C. I explained it last time, which is basically the sup of the norm x0 minus y, y belongs to C. So this is the radius of the smallest ball, okay, centered at x0, which contains C. That is exactly the meaning. Exactly the meaning. Okay? Is the radius of the smallest ball that contains C centered at x0. Are we in? So far, so good? Now, did I use the norm anywhere? Let's go back. So remember what I told you throughout these lectures. It took me 40 years to connect the dot, yes or no? So I don't want you to wait another 40 years, you, to connect the dot. I'm giving you this information so it saves you time. Am I making myself clear? But if I bother you, just tell me, I will move on. Okay. Let me go back. Where do we see the Banach space? Tell me. It's very, very interesting. I can continue with this, keeping an eye on 1965 or even 1975 with Karlovich. But what if I tell you where is exactly the Banach space? And do you understand throughout these lectures why I insist on this? Because my mind is not here. My mind is to try to work with other structures. Like I want to apply this on graph theory, for example. So I mean, it's not a Banach space. So you tell me, where do you see Banach space? I'm serious, by the way. Where? What is the element that uses the Banach space that I need to be careful about? That's what I'm trying to say. What do you think? Tell me. Huh? Yes? Anybody? So we have two spots that we have to be careful about. Spot number one is the weak compactness. Because once you are outside of the Banach space, you need to clarify this problem. Okay? Weak compactness. Is it vital? Yeah, because how am I going to prove the existence of minimal set? Number one. Number two is the conv. I need to pay attention also to the conv. Okay, the closest, smallest convex sets. So these two are there. Okay? What about what you see there? Is that a problem? Tell me about R0. Huh? Is a norm, but that is the distance between x0 and y. Yes? Therefore, I can replace that by what? By a distance. If I have a distance, I'm okay. I'm not using addition of the vectors as well as multiplication by a number. So I'm not using the vector or the linear vector structure of the Banach space. All what I'm telling you are part of these puzzles that you pay attention to them and you spend time reflecting on them, then you connect them. Then you have the big picture. If you don't have that, it's not going to work. You will always stay in generalizing metric spaces and doing contractions. You will never have the big picture. Am I making myself clear? Okay, so what does it mean, this R0? Now let's play with R0. In light of what I just said, let's reinterpret R0. Ready? Huh? Let me show you. So this, in fact, gives me C is included in the ball, closed ball. There is no open ball moving forward. Centered at x0 with radius r0. Do you agree? Yes? Huh? Okay. Now, let's take the image. Is included where? Who wants to tell me? I can't hear you, wallahi, I can't hear you. Tell me. Speak up, don't worry about it. Even if it's wrong, it's okay. Is it in the same bowl? Same bowl? You see? So T is non-expensive. So in fact, it's going to be in the ball centered x0 with the radius r0. Because T is non-expensive. Huh? T is non-expensive. Yes? Yes? So this opens the door to a new definition of non-expensiveness. So instead of having the distance between tx to ty less than the distance of x to y, if I have a concept of balls, if you give me a concept of balls, then I'm okay. I can define non-expansiveness using what? Balls. It's really crazy. Of course, what's in your mind? Balls means distance. But I can give you a set theoretical approach of balls without a distance. Do you see what I'm trying to do here? Is to open up. Start now to think outside of the box. Everything is up for question. Let's continue. Next. But the balls are convex and they are closed. Therefore, the conv T of C is in that ball. Yes? And what do we know about C? It is equal to the conv. Therefore, it is included in this ball. Now, what does it mean? It means for any y in C, the norm or distance T of x0 minus y less than R0, which means the sup of is less than R0. So, if I call this R0 R of x0, R being the Chebyshev radius, what we have here is R of T of x0 is less than R0. Yes? So, let us call now C star the set of all x in C such that the radius is less than R0. Okay? So R of x is the supremum, huh? The Chebyshev radius. R of x is Lipschitzian mapping with constant 1. Therefore, it is continuous. This function is continuous. And it is convex. It's a convex continuous function. Therefore, the set C star is not empty because x0 is there. It is closed. It is convex. You just proved that R of Tx is always less than R of x, the proof I showed you, because C is minimal. And therefore, it is invariant. Yeah? So we have what? C star closed. Because R is Lipschitzian through the triangle inequality. And convex, because R is convex. And T invariant. This gives me what? C star equals C by minimality. What does it mean? It means any x in C, R of x is less than R of x0. Okay. Does this imply R of x is constant? So this conclusion that you see at the bottom, does it imply that the function R of x is constant on C? Because if I take x0 was what? Does it have any special property x0? No. I just took x0. And therefore, this inequality with x0 being what, finally? Arbitrary. So if you have R of x less than R of x0 for any x0 for any x, it means that the function R of x is constant. That's Kirk, not Browder. Browder built another convex by reducing the diameter. Kirk did not do that. He showed, in fact, that R of x is constant. And therefore, so we have R of x constant. But wait a minute. In this case, the supremum, the infimum of R of x are the same. And what is the infimum? Infimum of R of x, x belongs to C. That is the Chebyshev radius of C. And what is the supremum? The supremum of R of x, if you put R of x, is going to be the diameter of C. So what did we found? We found, in fact, that R of C equal diam of C, and the Chebyshev center is the entire set. So this is what's known as C is diametral. When the radius is equal to the diameter, and it's not like, if you take the unit ball in little infinity, it is diametral, the unit ball. Anyway, so now we found the property on the minimal convex set. So we have a new theorem. What is the theorem? If the space does not have what? So we found that the minimal convex sets are diametral. Yes? Therefore, what is the theorem now? We have a new theorem. Okay? If we have a Banach space for which weakly compact convex subsets are what? Non-diametral, we made it. We have a fixed point. That is exactly Kirch's theorem. That is exactly Kirch's theorem. So how? What does that mean, non-diametral? Think about it this way. What does that mean, non-diametral? It means I can find an element in the set such that Rx is strictly less than the diameter. Yes? That's the definition of normal structure property. That's exactly the definition of normal structure property. So the normal structure property tells you only what? That weakly, I'm talking about weakly, of course, normal structure property, because we have this problem between weakly normal structure property and normal structure property. So focus on weakly normal structure property. Okay? It means any weakly compact convex set not reduced to one point has a non-diametral point. That's exactly the definition for normal structure property. Therefore, we found what? Kirch fixed point theorem. That's what it is. Nothing more. So when he put this theorem, people, what is this normal structure property again? Because they never heard of it before. So when they start looking at the normal structure property, it's opened a flood of questions about normal structure property in Banach spaces. If you go before 1965, you'll find zero. Nobody worked on it from fixed point theory point of view. Everything started in 1965. Now, we got to a point where people, because anything is related to normal structure property, anything is related to normal structure property. So people started to ask, maybe normal structure property is equivalent to fixed point property. To fixed point property. Equivalent, yeah. I witnessed this. People thought that. 1975. So now, Kirch's fixed point theorem, 1965. Now, we have to wait till 1975. Okay? People tried. Is there any other property of the minimal set? So we have K, let's say C minimal. Yeah? With diam of C greater than 0, meaning more than 1 point. C is convex, closed, bounded, because it's weakly compact. What did we prove when we started fixed point property in Banach spaces? Do you still remember? If we take a non-expansive map in a Banach space defined on closed convex bounded set, non-empty, what did we prove? That's how we started. It was known before 1965 anyway.
We can construct new T epsilon, which is contraction.
Which will lead to what?
One fixed point.
Yes, but it will give us what?
An
Approximate fixed point sequence. So C, so there exists an approximate fixed point sequence xn in C. What does it mean again?
xn minus txn plus 2.
Good job. Limit xn t of xn equals 0. Yes? Now, let me come up with a new function. Remember the function I used was r. Yes? Now I want to come with a new function. So you tell me. This is Karlovich, by the way. Huh? So how would you define? I'll give you a hint, but it gets complicated. So I'm going to define the new function, which is limit norm of xn minus x. And let's call this one phi of x. The problem resides where?
Limit may not exist.
Is the limit. What do you mean by limit? Right? Because I didn't say anything about what?
Xn is converted.
About xn. It just belongs to C bounded. So how are you going to define this object? So according to Karlovich, the way he bypassed this problem, he used the Banach limit. Have you heard about this? Okay? You should read about it. Okay? Banach limit. And they write it as lim L-I-M capital. Banach limit. Are you with me? Now, let's ask my assistant. Let's see if I have the internet here. One second. Do I have the internet? Oh. Why is that? Okay, fine. Just give me a second, and you will see why I'm doing this. Okay. 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 Ready? Tell us, first of all, let me be polite with him. Okay. It's slow, the internet, that's why. If it takes long, I will move on. Ah, hi, how is it going? Okay, good. Good. Enjoying some good time. I always do this, some good time at Aligarh. Okay. Because he needs to know me that I am the one, not somebody else, because my daughter is using it. Okay, now, tell us about Banach limit. Okay. So here he's going to explain to you how to build Banach limit. That's how Banach did it, by the way. Okay? How he came up with the concept of limit. And what's interesting is only for bounded sequences. And what's interesting, it extends the normal limit. So instead of saying there exists a subsequence, you avoid to say that there exists subsequence. Therefore, for my function, I can use Banach limit. I avoid to talk about what? To subsequence. And we know that the Banach limit is always between lim inf and lim sup. Okay? There is another way you can avoid all this, but it's fancy. It's through ultrafilters. Okay? Because in a compact set, sequence in a compact set will always be convergent along an ultrafilter. Okay? Ultrafilter. And therefore, if I use limit over an ultrafilter, again, I can avoid what? The problem of there exists a subsequence, blah, 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 blah. And of course, the third option is to consider the lim sup. Okay? That is also a viable condition to do. Anyway, so and the reason, by the way, the reason I wanted to do this exercise is not to impress you. Oh, no, no, no. No, 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 absolutely not. I'm too old for this. I don't want to impress anybody. It's to encourage you to use what? To use this AI assistant. And don't use the free one. You are not going to get anything with the free one. You need to get the plus. Okay? All my work is done now with this assistant. Okay, so let's go back to our problem. So let's use lim without being precise, huh? Okay? So what do we know about this function? But this function is, again, Lipschitzian mapping with constant 1, therefore it is continuous. Okay? Number 2, it is convex. Number 3, which is far more important, what if I put here t of xn is going to give me the same value. Why? Because xn minus t of xn goes to where? To 0. Okay, so now look at this now. Fix x0. Fix x0 in C. And put R0 equal phi of x0. Yes? And then consider this C star x in C such that phi of x less than R0. Do you see how? Then what happened? C star is going to be convex, closed subset of C. And it's not empty because you have x0 in it. And because of phi of x is less or equal, see, if you put x, okay, let's do it, let's do it. What is phi of x? Lim norm t of x, sorry, t of x equal limit, because it's an approximate fixed point sequence. Yes? And now I can use what? Non-expensive. So phi of t of x is less than phi of x. Therefore, C star is invariant. So what happened? We can use what? Minimal what? Behavior of C to say that C star is equal to C. What does that mean? It means for any x in C, phi of x is less than R0, which is phi of x0. Same argument because x0 was arbitrary anyway. Therefore, the function is what? Constant. The problem is, what is the value? Where are we now? C is weakly compact. I have a sequence xn, therefore, there exists what? A subsequence, which is what? Converges weakly. Let's call omega the weak limit. using what? The lower semi-continuity of the norm, we get what? That. So omega, sorry, there exists omega, a weak cluster point of xn. Therefore, omega minus x is going to be less or equal than the limit of the norm of xn minus x. I'm talking about this limit. If you are using an ultrafilter, and because we are in a weakly compact, omega is the limit, the weak limit over the ultrafilter. If you are using the Banach, then any subsequence, the limit over the subsequence will be smaller than the Banach limit. You see, it adjusts, but really it's no big deal. So now, for every x, and this is phi of x, and it's constant. What you have there is phi of x, and phi of x is constant. So this is your phi value. But what is the supremum of omega minus x for x in C? But that's the radius. And we just said what? That is equal to what? The diam. But wait a minute. What is phi again? Is the limit of xn minus x is less than the diam. Therefore, this tells me what? That phi is equal to what? Diam of C. Now, this is Karlovich lemma. Karlovich lemma is telling us that if you take any approximate fixed point sequence in the minimal set, and you take any x in the minimal set, the limit will be exist and is equal to the diam. Okay, we used it from 1975 all the way to 1980 something. Now comes Bayon. And that's why I send you this paper, because it's really beautiful to all of you. What did he see, Bayon? He saw something, honestly, I let it go because I'm not working on this for quite many years, in fact. Many, many, many years. Almost 30 years I didn't work on this. But this is what he saw, Bayon. Of course, we used it. Oh, we used this Karlovich lemma, 1975. And I believe it was 19 what? What is it? 1980 what? I forgot. 81? Yeah, check it, check it. Give me the year so it gives you an idea how many years it took. So what did Bayon, Schoenberg, they saw the following. How did we build again the approximate fixed point sequence, Izhar? How?
We can construct with the help of a non-expensive map contraction, construction piston.
Okay, how did we build the contraction? T epsilon.
81, sir.
19 what?
81, sir.
81. The name, the other name is complicated, Schoenberg, so that's why epsilon z plus 1 minus epsilon t of x. Okay, let's take epsilon. It's a contraction, it has a fixed point. Let's take epsilon equal 1 over n, and xn is the fixed point. Ready? I told you about this anyway. So we have xn equal what? 1 over n z plus 1 minus 1 over n t of xn. And obviously, I showed it to you too during the lectures, that xn minus t of xn goes where? 0 as n goes to infinity. What I did not show you, what did Bayon see, is that in fact, and I leave it to you to do this as an exercise, xn plus 1 minus xn goes to 0. Oh. So it did not just prove that xn is an approximate fixed point sequence. He showed that this sequence satisfies that second condition. Now, what is asymptotic normal structure property? So we have a theorem, new theorem. True. What is it? You assume that if C is invariant, I mean, closed, bounded, convex, weakly compact, T, non-expansive. If Xn is an approximate fixed point sequence such that limit xn plus 1 minus xn equals 0, look at now what he did. He assumes there exists an x. Then there exists x in C such that limit of xn minus x less than the diameter. I mean, not only C, and any C, which is T invariant. So he wanted what? To violate what? The property that he discovered. And that's, he called it asymptotic normal property. Asymptotic normal structure property. Let me 2 minutes and I will stop. Now he takes L2, James renorming. What was it? L2 and the new norm, beta positive, I mean bigger than 1. Max, norm 2, beta, norm infinity, soup. Okay? Then, norm beta is bigger, norm 2, less than, beta is bigger than 1. Huh? So otherwise I will put max between 1 and beta. 2. So norm beta is equivalent to norm 2. Is an equivalent norm on the Hilbert space. Why did James come up with this renorming? For beta equals 2. Okay? So for beta equals 2, norm x, I'm sorry, L2 with this new norm fails the normal structure property. Sorry. So the L2 with the new norm fails the normal structure property. Why? Because they said that the normal structure property is satisfied by any reflexive Banach space. What did they tell you? 1965. People did not know about what? About normal structure property. It was brought in by Kirk. And therefore, the people working in Banach spaces, they start asking questions. That's how we do all the time. When we don't know, we start asking questions. So they thought, oh, maybe any reflexive Banach space satisfies the normal structure property. So James told them, James is very famous, by the way. Very famous. Especially James spaces, you should read about this business. So James told them, no, that's not true. And here is a counterexample. How did he thought about it? Don't ask me. It's crazy. Sometimes it's really crazy. Now, what did Bayon do? Bayon showed, and in fact, it was also known that if beta is less than square root of 2, we have normal structure property. Okay? And that was an answer that I answered to Mohammed Amin yesterday, is that you can go all the way, according to Banach-Mazur distance, all the way to square root of 2, and you still have normal structure. You have even uniform normal structure property. Anyway, So what did Bayon do in this paper is that beta between square root of 2 all the way to 2, we don't have normal structure property, but we do have asymptotic normal structure property. That was the essence of that paper. That's exactly the essence. Now, what's amazing in that paper, and finally, again, it's confirmed. I mean, I remember it when I was a student, to be honest with you. That was almost 40 years ago. It's confirmed that for beta equals 2, he proved it. They proved this in that paper, that we have fixed point property, which means that this asymptotic normal structure property is not equivalent to fixed point property. What happened for beta bigger than 2? It says there that Bayon was able to prove for some special values of beta. That he told me himself this. But he was never able to prove it for any beta. So anyway, what's the conclusion? If you can find anything about the minimal set, you have a big theorem. Thank you very much. I wanted to talk about another part, too much. So I want to stop here. Yeah, I'm gonna stop.
Okay, Professor Amin, thank you very much for your this lecture series for last 4 days.
I will have a PDF for this. I can save it as a PDF and send